Hello, everybody. My name is Norm Johanson. I am a senior dev at AWS, Amazon Web Services, where I focus on all of the .NET tooling for AWS. And today, what I want to talk about is what is a serverless and compute environment? We're going to define what that is, and then what is the AWS implementation of that. And then we're going to do a similar thing with containers. But now containers is a very large subject, so what we're really going to focus on is enough of containers so that we can compare that with a serverless environment, so we can learn how those work. And again, we're going to look at what are the AWS offerings for container environments. My ultimate goal, though, with this talk is to help give you the information of figuring out which of these technologies to use in your applications. As containers and serverless has gotten more and more mature, there's a lot of gray area when you might want to choose one of these, and hopefully this talk will help you out. So when it comes to choosing the tech for your application, there's a lot of reasons. Most of them fall down to two fulcrums. Does the technology solve the requirements of my application? And the other fulcrum is what is the cost of this technology? And that can be broken down into what is your operational cost, and as well, just as important, what is the engineering cost? We as engineers are often the most expensive resources in our company. So anything we can do to save our time, it reduces the cost of your technology. So for serverless, this is what I think is the three main factors when you're defining what a serverless environment is. It supports continuous scaling, meaning it's always providing the scaling for the application's needs right now. It's not listening to see how it's going and then deciding when to adding more resources there. It's just always providing the compute power needed for that moment, meaning scaling up and scaling down. Now, it's called serverless, but there really still are servers running in the background. There's no magic there. But again, we don't have to manage any of those servers. We're not having to make sure anything is all patched up and running, making sure they are still up and running. That is all taken care of us by the serverless environment. And because we're not managing any servers, we're not paying for the cost of having servers up and running. We're paying for just how long it takes to run our code. So our cost factor is just on our code. Now at AWS, we have AWS Lambda. That is the main service for the serverless environment. It provides the compute power. You deploy what's called a Lambda function to AWS. It is an event-based system, and that's how it provides that continuous scaling, because it's always providing the scaling based off the events that are coming into your Lambda function. And those events can be coming either from the HTTP events via a service called Amazon API Gateway, which allows you to expose your Lambda functions to the web. Also, many AWS services will also send out events for when state changes. For example, when Amazon S3, the object storage system, or Amazon DynaDB, the managed NoSQL system. When the state changes in those systems, it will send off events. And you can configure so that a Lambda function is going to respond to those events. So this is how you can sort of build applications just based off the events coming from services without ever having to manage any servers. You can also write custom events as well, and then invoke your Lambda function with those custom events with any of the AWS SDKs. Configuration is very minimal. There are a few more settings here, but these are the two most important ones. Memory, which also indirectly decides how much CPU power your Lambda function gets. And so memory is really the vertical slider, or the slider for your vertical scaling of your application. And then the other option is timeout, because Lambda is not meant for long-running processes. You're going to take an event and process the event, and then that function is done. So the max timeout in Lambda is 5 minutes. And this is to help guard you in case you accidentally cause an infinite loop and your Lambda function runs forever. Because remember, you're paying for how long it takes to run your Lambda function. For Lambda, we support .NET Core, which is the one I care the most about from the .NET team. We also have Node.js, Go, Python, and Java. So I want to kind of describe what happens under the covers of Lambda. This isn't the exact science. This just gives you an approximation of what Lambda is actually doing when these events coming through, so you can understand the life cycle. So the first thing is we'll get some event. Maybe this is a service event or a web event. It comes into Lambda, and Lambda says, oh, I don't have a compute environment for this. I'm going to go as that event, and I'm going to create a compute environment to handle that event. And it's going to go process that event. So during that cold start, it got and procured the compute environment. It started up the .NET runtime. It started up my code, and has actually responded to that event. Once it's done and there's no more events coming in right now, Lambda's just going to freeze that compute environment. Now, when it freezes, it's freezing that whole .NET runtime. So this means like any of the statics you might have set up, any global initializations still exist in that frozen compute environment. So when new events come through, it'll actually be able to reuse all that stuff. So this is how you can cache information per request. But you need to think of these, though, as still a stateless compute environment, because there's no guarantee you're going to go back to the same compute environment. So we'll get our next event, and Lambda will just say, OK, I already have this frozen one, so let's just go thaw that one out and process our event there. And that's called that warm start, where it doesn't do all that initialization work, and it's just going to easily just execute that already on that compute environment. And once that's done, and there's no more events, it'll go and freeze that again. Now, what happens if we get multiple events? Here we got 2 events coming into our Lambda function. So Lambda's going to take that in and says, well, I can just thaw out the first compute environment, but we have no idea. Is this going to take 10 seconds, 5 minutes? We don't know. And we don't want any of that to bottle up. Lambda is all about horizontal scaling. So what it does is it's just going to go and create another compute environment. So it's going to do those both in parallel. And this is where Lambda gets that really good horizontal scaling, where it's just by the events coming in, it'll do that continuous scaling based off those. And when there's no events, it'll just freeze those compute environments. So once those are gone, not being used, they'll be frozen. And after some amount of inactivity, Lambda's just going to go reclaim those compute environments. Now, the important thing to think about, everything in that group box there is completely abstracted from you. In a serverless environment, everything is managed for you. You're just sending events for you, and you're paying for how long it takes to run your code. The compute environments are all abstracted away. For .NET Core in Lambda, right now we support .NET Core 2.0. 2.1 came out a couple weeks ago, and we're quickly working on getting that one out. What you do to create a package bundle is basically you could use the .NET publish command. This is on the CLI, and that'll create a folder with your DLL and all your dependency DLLs. Although I would highly recommend using one of our tools to create this deployment package. Either our Visual Studio Toolkit, or we have a NuGet package out there called Amazon Lambda Tools, which is a project extension to the .NET CLI, so you can still do that same deployment from the command line. The reason I recommend doing it this way is by default, .NET Publish is going to create you a package bundle that's portable to any platform. So it's going to include all your Mac dependencies, your Windows dependencies, and Linux dependencies. When you're deploying to Lambda, we know this is a Linux environment. So we will direct .NET Publish to make sure, let's optimize this package for that Linux environment, which will create a smaller package bundle. And the smaller the package bundle can reduce that cold start time. Now, the programming model is pretty simple for Lambda. We didn't really want to design any large frameworks. We really wanted to just keep this as just write your .NET code. So all we really say is pass us the function handler string that identifies what method to call. And that string identifies the assembly and the type and the method. And it's saying, what's the .NET method? Which means it can really be any language that supports .NET Core. C#, F#, VB, Core, all those languages are fine. The signature of that method is pretty flexible. You can have a method that takes no parameters. Maybe you have a Lambda function that you just want to call on it with no input, and it's just like once a day to go clean up some data. So you could have a Lambda function that's no parameters there. You probably will also take one parameter, which is the event coming in. In this case, it's the S3 event. And optionally, you could take in an iLambda context object. That context object provides information about the Lambda runtime, as well as some APIs to do some logging. Methods can also be asynchronous. So in that case, you would just return back a task. And Lambda is essentially going to wait for when that task says it's complete to know when your Lambda function is done. One of the interesting things that we've also been working on is the ability to run a serverless ASP.NET Core website. We do this we have a NuGet package out there called Amazon Lambda ASP.NET Core Server, which essentially bridges the gap between Amazon API Gateway, which is your REST front end, with the ASP.NET Core framework. So it marshals the requests back and forth. And so some of the pros of doing this is, well, ASP.NET Core is a very powerful framework. It's constantly getting new improvement. Most of you probably know how to use this framework, so there's little new to learn. And it's also easy to migrate existing applications to this. Some of the cons are this could produce a larger package bundle, although with .NET Core 2.0 and the upcoming 2.1, the ASP.NET Core dependencies are actually already pre-installed on the Lambda target environment. So when you run .NET Publish, it won't actually include any ASP.NET Core dependencies because it knows they're already on there. So your package bundle actually usually isn't going to be too much bigger. The other con would be cost to initialize the ASP.NET Core framework. And this is going to happen every time one of those compute environments is created. That first time it's created, it'll initialize that framework. So this is where you have to be strategic on how much work you want to actually do in that startup CS class. So if you have a very large monolithic application that has a lot of things going on in the startup, this might not be an appropriate use case. If it's a pretty lightweight application with only a few things going on there, this can be an easy way to just transition your ASP.NET Core applications to be a serverless platform. All right, so we've talked about the slides. We just did some ASP.NET Core talk. Let's see what it would take to actually do that. So if I'm in Visual Studio, this window over here is our AWS Explorer from the AWS Toolkit for Visual Studio, which you can download from the Visual Studio Marketplace. And we can create new Lambda projects by going File, New Project. And under C#, we have some project templates here. Again, we said we have F# support, so if we go under other languages, we have AWS Lambda under F# as well. So same project templates. So the project templates really break down into two different styles. There's the Lambda project. This is where you want to write a single Lambda function, deploy it to the Lambda service, and then you will manage connecting it up to whatever's your event source. The other option is you want to deploy it as a serverless application, which means you might want to write n number of Lambda functions and deploy them all together as one unit, along with other AWS resources. And you do that with what's called a CloudFormation template. It's a JSON or YAML file that says I want to deploy all these together. So because we need to deploy our Lambda function and we want to set up API Gateway for our ASP.NET Core application, we're going to choose the serverless. And we have some initial blueprints to help get started, one of them being the ASP.NET Core blueprint. So here's our project, and this is just a regular ASP.NET Core application. There's not very much different about this application compared to your new ASP.NET Core project you would do from Visual Studio. The two main differences is typically an ASP.NET Core project has that program CS file to do the bootstrapping. That just got renamed to local entry point to identify this is the code when I'm going to do F5 and just debug this locally. This is what's going to run for debugging locally. Then there's the Lambda entry point, which essentially is the replacement of that for when you're running serverlessly. So this is the code that does the same job as that local entry point. What it does is it's extending from a class from that NuGet package. And that NuGet package, that base class, let me shrink this down a little bit, has this function handler async. So that's the actual Lambda, the actual .NET method that we want Lambda to call when our events come in. And that's what's going to take care of initializing the ASP.NET Core framework on the first request and in handling all the marshaling of the requests back and forth between API Gateway and ASP.NET Core. Then the only method we actually have to override here is the init method to identify what is the startup class. So this is the only code that I have in this project that is specific to Lambda. Everything else in this project is just standard ASP.NET Core work. So I'm going to just go ahead and deploy this project, and then I'll take a look at the CloudFormation template as it's deploying. So you can right-click on the project, and there's published AWS Lambda. You also might see there's the published AWS Elastic Beanstalk. Elastic Beanstalk is the service you would use to do more of the traditional deployment, where you want to go deploy this into an IIS environment. So both those show up because this is a web project. So we're going to choose Lambda. And so with CloudFormation, which is our vehicle we're going to use to do this deployment, you create a stack, and that stack represents all the resources. So we're going to name that stack. So we'll call this NDC Oslo 2018. And then we need to specify an S3 bucket. Let me set that up. So the reason we set the S3 bucket is when we do deployment, we're going to build that package bundle, upload that package bundle to S3, and then update our CloudFormation template to say the code for these projects, these Lambda functions, is in that package bundle we just uploaded to S3. So I'm going to push publish. And so here we're just really running .NET Publish, which is going to create, again, optimized for the Linux environment. It's uploading it to S3 now. And now it's telling CloudFormation, go start creating a stack for us. And so that's going to bring up our CloudFormation view here in a second. There we go. So this view is going to start sending out events as these resources come online. And I could define my whole application in this. I could define databases and S3 buckets and all those things. My CloudFormation template is actually quite simple. I just have the one resource here. This is my serverless function here. And here is that handler string that I talked about that identifies in the package bundle what we're actually going to call in that method. And a serverless function resource is actually a bit of a meta resource in CloudFormation because it actually creates, it gets converted into other smaller resources. In this case, it's going to also set up our API gateway as well. So here we set our runtime. But in the events section is where we actually say we're going to set up our REST API. So we're going to have two endpoints here. One is for everything coming in at the root of our REST endpoint, send to our Lambda function. And then the second one is really just covering the other case of anything past the root, as we also want to send to our Lambda function. The reason we're doing this is because we're going to allow ASP.NET Core to handle the routing to our write code. It's going to figure out what's the controllers and all those. So we're going to take advantage of that. So that probably is going to be, yep, we're deployed now. And that takes just about, in this case, it was pretty simple. It took about a minute to do. We can click on that link, and we should see our application here. So here is our ASP.NET Core application as a serverless application running out there on Lambda and using API Gateway as our front end. Okay. So now that we talked about what is the serverless environment and what is the AWS implementation, let's switch now to talking about containers. And by containers, I'm focusing on Docker. I know there's other container technologies, but I'm just going to focus on Docker. And again, containers is a very large topic. So my goal is to talk about where things are similar and different with a serverless environment. So our benefits for containers is we have a rich, powerful tool set. We have the Docker CLI. We have our image registries where we can easily push our Docker images around and pull them around. It's also cloud or on-premise agnostic. So this is technology if you want to make sure you're not locked into anything. Containers keep you away from that. The application packaging, it's creating Docker images, allow you to make sure you got everything logged to the versions you want, including what your application dependencies are, your runtime of your language and your OS, all that gets logged in there because that image contains all those dependencies together. And Docker does also allow you to easily spin up new containers and tear them down. So it provides that fast deployment and scaling. Now the major parts of a container application, we have, again, our container image, which is that immutable image of our application. We have the Docker runtime, which takes care of running our containers on our host machine and having it communicate with that. And then we have the orchestration. So most likely, we're going to want to be running our containers in a highly scaled environment, not just on one machine. So we're going to have orchestration to be able to push our containers across a fleet of machines. Now, if we compare the container images versus the Lambda package bundle, again, the container image contains all the bits. So it contains my whole application. It contains a .NET Core runtime. It contains the Linux dependencies if we're doing Linux. So that image is typically about 100 to 200 megs for a .NET Core Linux image. Now, if we compare that to a Lambda package bundle, that is just a zip file of just your application dependencies. And typically, that is just a few megs. In fact, if we looked at what ours that we just created was, here, the application I just did was 600K. So that's the whole application bundle for Lambda's case. And when you want that to be small for Lambda's case, so it can give you that really fast cold start. In fact, Lambda's max size for a package bundle is 50 megs. Now, orchestration is where things, I think, get a little more complicated in the container world. Versus in the serverless world, we have everything is just being managed for us by the service. The orchestration's job is to basically replicate all that same work. It takes care of all of our scaling needs, adding and removing containers. And it's not just doing this based on the events coming in and adding compute environments. You have to have some sort of metrics that determine when you want to add and remove your containers. Whether that's CPU usage or requests, you have to make sure that those are set up correctly so that your orchestration system knows when to add and remove environments. It also takes care of your durability and placement, right? So we might have 10 machines set up in our cluster, and we start launching an application that says, let's have 3 instances of this container across our cluster. The orchestration system is to make sure that you don't just put all 3 on the same machine, giving you a single point of failure. It makes sure that those containers are spread out across your fleet. And because our orchestration system is probably going to have lots of other microservices on there, you're probably going to need to have some sort of service discovery system to be able to find those and communicate with them. So that's the orchestration system's job. Now, the orchestration system is relying on your container cluster. That means the actual servers that are going to run your containers. In AWS Lambda, that would be EC2 instances. And you want to make sure that those servers are spread across multiple data centers. So if there's ever a problem in any one data center, again, things would fall over to the other machines. In AWS, that would mean you would deploy these EC2 instances in different availability zones. So AWS is broken up into regions, and then every region has broken up into several availability zones, so you can have that redundancy within a region. Now, most orchestration systems will have some combination of a managed or unmanaged environment. And this is where I think things have gotten more gray area between comparing serverless and containers. With having these managed environments, there is that idea you don't have to manage the servers like a serverless environment. But there still are some more differences. But you can also do unmanaged if you want to be in complete control of how your machines are set up in your machine and when they're taken on and offline. Now, AWS, we have a lot of services that rely on containers. We're going to cover some of them here. First one I want to talk about is AWS Batch. I thought this was interesting to talk about because it kind of solves one of the things that serverless isn't really necessarily great at, which is I have some long-lived process that I want to go do, maybe a long log dive through some work. So batch processing is not the greatest in a serverless environment unless you can break up your batch processing into multiple events. Depends on your system. But we can also just use AWS Batch to do those processing. So batch allows us to essentially define a job, and the job just identifies what container you want to run, and you could pass in parameters to that container. Then you would set up queues. So I could have, here's my normal queue that I send everything to, but I have my high priority queue. So when my boss comes to me on Friday afternoon and says, I need some data right now, you could submit a job that just goes into the high priority queue, so it would jump ahead in line. And then you have a compute environment, which is what your queues are going to be tied to. And again, you can have managed compute environments or unmanaged compute environments. And the managed compute environments, in this case, have an interesting feature where they can use either on-demand EC2 instances, which means it's just going to create EC2 instances as needed, and it's going to do that with whatever's the current pricing for those EC2 instances. Or you can say, I want to use spot instances. And what spot instances is really good for is when you might have some batch work you want to do, you don't necessarily need it right now. You just need it to be processed at some point. So you could say, I want to run this batch job and use these spot instance fleets. And what AWS does, it says, well, there's always a varying degree of demand on a region, depending on even the time of day, right? So at 2 in the morning, when everyone's gone to bed, the internet usage goes down. So what AWS does is it's going to actually have what they call spot instances, where they will temporarily lower the prices down, and you can take advantage of that. So I could say, let's use my compute environment uses spot instances and use these when the price is currently 80% of the current on-demand price. So it's a way you can run your batch jobs and save money on that. All right, so let's take a break from slides and do another demo. So the problem here is, that for this demo, we're going to say is our boss has come to us and says, we need to do an audit. I need to know, over the past year, how many Lambda functions you've created and what type of compute environment, what runtime did you use? Did you choose .NET? Did you choose Go, Java? So we need to go find that out for him. Now we can do that because some of those Lambda functions we probably deleted, so we can't just see what's currently deployed, but we can use a service called CloudTrail, which actually creates an audit trail of all of your API calls for most of the AWS services. So it'll record the whole entire log and write that out to an S3 bucket. When it writes to an S3 bucket, it's going to write it into a file with this file format. So S3, you put a file in there with a key. That's how you get it back out. And you put it into what's called a bucket. And so that key format is going to be AWS logs, my account ID, CloudTrail, the region, and then there's the date part of the key, and then the final file name. So the fact that I got the date in there can make it really easy for me to parallelize this work. So if I say I want to do this for the past year, I can just say, well, let's run a job for each one of these days based off of that date factor. So let's go take a quick look at our code here. So here's some code I wrote. I did hard code some things. I should definitely parameterize it. And then here is my S3 bucket CloudTrail. So you can see here, I've got logs. I have logs for the last 3 years of all the API calls I made in this region. So what we're going to basically do in this code is we're going to go list all the objects based off some prefix. When you do a list objects in S3, you can say, give me all the objects where the object key starts with this. And so we can determine what that key prefix is going to be. If we look at that code. So when we run things in batch, it sets an environment variable for an array index, because I'm going to run this job as an array of 365, so one for each day, and it's going to set this index on here. And so I can use that as an offset off the current day to just go compute that day. And that's how I'm going to set up my prefix on there. So that's how I know each one of my containers is going to go process 1 day's worth of data. I'm not going to go too much through the rest of this code. I do have a link at the end that's going to have the slides in this code if anyone does really get curious about this code. But basically, it's just going to go loop through all the objects. We're going to parse all the JSON out of there to find out if it was our actual Lambda function, and add that to our counter. And I think just to show as a reference, if we went to the CloudTrail console, so this is the console that can do some diving for us. So we can say event name, create function here. So here's some data. This is when I was practicing my talk the other day, it looks like. And we can look at the raw JSON here. And you can say, this is what's actually written by CloudTrail for all of the API calls. So it's going to identify the user in my account, the service that actually did this, since I deployed this through CloudFormation. So I could go identify that this was actually created as part of a CloudFormation template. There's identifying the service that this is and the actual method that is on. And then here are all the parameters that was set as part of the API call. And you can see there's the runtime. So that's what I'm going to go parse all my JSON to find that information out. At the end of that, I'm going to go write all that data I'm going to persist it out to my DynaDB table. And so this table is very simple. Since this is a NoSQL system, all it is a table with a key of runtimes. It's no attributes. The attributes will create it as we're saving the data. So to run this in batch, first I need to publish the container image. I can do that in Visual Studio by right-clicking on this and say Publish Container to AWS. I'm going to just leave all this at the default here. This is going to push our image to Amazon Elastic Container Registry. That's the service that we have for your containers. So this is going to do the whole Docker build for us. It's going to log on to ECR, and then it's going to push that image. I've already pushed this a few times in practice, so most of that image is always there. And if you know a Docker is always just pushing the layers that have actually changed between your pushes. So now that's there, I can go grab my name of that container image, and now let's switch to the batch console. And so I'm going to actually skip the Getting Started wizard because I want to show the components that make this up. So here we're going to create our compute environment. And here, this is where, again, I can have a managed or unmanaged compute environments. I'm going to call this my NDC Oslo compute environment. So if you never used AWS before, one thing you should know is AWS will never do anything in your account unless you explicitly give it permissions to do it. It does this through a vehicle called Identity and Access Management Roles. So in this case, the batch service needs to make other calls on my behalf because it needs to go check to see, do I need to go adjust the amount of compute power in here, and do I need to create new EC2 instances? So in order to do that, I have to assign a service role that grants it permissions. And in the console, if I would have new, it would have created this default one. But this is what this is it's always, you have to give it permissions to do things for you. And also, on those EC2 instances, there's going to be an agent on there, which is going to go reach out to write log files. It's going to reach down to go pull down our Docker image from ECR. So that agent needs permission. And you do that with assigning an instance profile to your EC2 instances. And that's what this is here. So I'm going to set that to the default one that they'll create for us. And I think all the rest, I'm just going to leave the defaults here. So my minimum is going to be 0 virtual CPUs, so I'm not going to have any machines on it now. And the max, I'm going to let it at 256 virtual CPUs on there. So but I'm going to just leave everything else at the defaults. So now we have our compute environment, which doesn't actually have any machines to it. So now let's go create a queue. So we'll create our queue. Call this NDC Oslo queue. We'll set a priority. The higher the priority, is the higher the number, the higher priority. And then we're just going to assign a compute environment to it. So the one we just created. So now we have our queue set up. So now when you're going to go create our job definition, I'm going to create that. So we'll call this Cloud Trail Search. Now this is going to be running. This represents our running container, and our container has to access S3 to go download those objects, and it has to download or has to write to DynaDB. So this is where we need to assign a role to give permissions to our code running in there. And so every job could have a different set of permissions there. So you're not just going to create one role for every job that you run in your batch environment. So I've set that up. I got my batch demo role. I'm going to identify the container. I'm just going to call this. This is the Docker image that we just published to ECR. And then the work that I'm doing in my container, my batch is on a per day is pretty minimal because it's really just doing an S3 list and looping through those things. So I think I only need 1 virtual CPU for that, and I only need about 256 megs for that is my guess. So by shrinking that, I'm allowing more room on my batch cluster by doing that. And all the rest, I'm going to leave defaults. I could definitely pass parameters and other things here, but my case is pretty simple. So now let's go ahead and submit a job. So NDC job. We'll select our job definition that we just ran. There's our queue that we done. I'm going to say I want to run this as an array of 365, so I can have one for every single day of the past year to do all that processing. I can also override any of the settings of the batch job definition here, but I'm just going to leave all those at the defaults and submit that. And so now batch is going to now take that job. It's going to then eventually go find out we need to go add more compute environments for this and spin those up and run those up. So if we clicked on this, we should see. Now we have 365 jobs all in the runnable state. They're waiting for a compute environment to become available so they can run. So if we were to go look at EC2 console, this might show those up, but it might not yet. Depends. It takes usually a minute or so for batch to start doing the recomputing. So it hasn't done it yet, but in about a minute or so, it's going to start spinning up those instances. So we'll come back on this demo again to check the results of this demo now that we've got everything deployed. AWS code build, so this is our code build service, and that is actually built around containers as well. When you do a build in AWS, it's really spinning up containers for that, and you run your build scripts on that. We support .NET Core 2.0 as one of our managed images on there, as well as you can bring your own Docker images as well. So if you have technology that's like not part of the .NET Core base image, you can do that. 2.1 will be added to there soon. The difference between using one of our managed containers versus one is if you're pulling one from Docker Hub, that means the first time you're going to start up your build environment, it has to download the image all the way from Docker Hub versus from ECR where it's co-located in the same region so the download can be faster. You can also use this service to build containers as well. Now, Amazon Elastic Container Service, or ECS, this is really the general purpose orchestration system that we have at AWS. It's what other services are actually built at. In fact, when we created our batch compute environment, what that really did, if I switch back over, is it actually created a ECS environment for us. It's managing that there. So ECS is really sort of the general purpose building one block you do. So the way ECS works is you define a cluster, and that cluster is made up of container instances. These would be EC2 instances. Then you would have a task definition. This task definition identifies all of the containers I want to deploy as part of a task, along with all the settings that you need for that task definition. How much memory, how much CPU you want to dedicate to each of those things. All those settings are set as part of that. With a task definition, you will go say, I want to go run n number of tasks on my cluster with this task definition. And ECS is going to take care of, you can see in that picture, of spreading those containers across our machines. Now, when you do this, where you're running a task directly on a cluster like this, this is more for transitory processes, kind of like our batch job. Like when the process declared in that container image is complete, you want your task to end. It's not something for when you want to do like a web server, something that's long-lived. We'll talk about that in a second. But so once those tasks start up, they're going to reach to their container registry, whether that's Docker Hub or ECR, and download that image and then start that task up. Now, services is the other way you could run a container application on ECS. And this is what you'd want to do for your web servers. Because with a service, the service is going to monitor the health of these containers. If these tasks die, it'll go and create new instances of those. So the service will go and spawn off a bunch of tasks on there. And if these are web servers, we don't want 5 different endpoints for our web application. So what we're probably going to do is create a load balancer, and the service will take care of registering all of the healthy tasks to our load balancer. And then once those are registered and they're healthy, then the load balancer will send the traffic evenly across all of our deployed tasks for our service. Now, there's actually two ways you can run tasks on ECS. You can run it on EC2 instances. So this is when I created my cluster. I've created some EC2 instances, and I've assigned those EC2 instances to my cluster. The other way is with Fargate. So when you launch your task, you say, I want to launch this as a Fargate, and Fargate will take care of procuring all your compute resources for you. So you'll just say, I want to launch this as Fargate. I need this much CPU and this much memory, and just go. And so it'll actually automatically spin up those resources for us. And then once you've stopped that service, it will go and tear those down. So now you get back into that where there's no service to manage here. The servers are managed for you by the service. And so the cost is going to be for this is based on the task duration. So unlike Lambda, where you're just basically costing how long your functions run, and then if they're not running, there's no cost because there's no cost for idle functions. In this case, as long as your task is running, even if it's not doing anything right now, you're still paying for the time it takes for those containers to be running. And it's based off of the CPU and memory you allocated for your Fargate tasks. Now, I can't talk about orchestration systems without mentioning Kubernetes. Kubernetes is definitely quickly becoming the standard across all of the orchestration systems out there. Seems to be really leading over Docker Swarm and Mesosphere. It has the largest community behind it, and all the major cloud vendors and in tech industries are basically getting behind it. So Google, AWS, Microsoft, Red Hat, everyone is contributing to this one. It can be quite a bit more challenging to set up. There are a lot of tools to help that out. If you're using AWS and you want to set up your own Kubernetes cluster, there's the tool Kops out there, which you can use to get everything set up for you. Also, every major cloud vendor is also working on making a managed Kubernetes environment. AWS just launched last week the Amazon Elastic Container Service for Kubernetes, EKS. So that just came out. I didn't get a chance to really update my talk based off that because they surprised me with that coming out. There's also an AWS workshop for Kubernetes if you want to get a better understanding of how you can use that. That is a workshop based off Python, but all the ideas are the same about how you manage your Kubernetes. Now, even though I think Kubernetes is becoming the standard, I don't think that this replaces ECS. I think there's a place for both of them. It depends on what you want in your team. Kubernetes is a very powerful system. It's got a lot of plugins for you. It's open source, but it is a bigger thing to get involved with. You have more to manage, more to set up, more to learn. ECS is an easier system because it's a fully managed container system. It can do everything deployment. In fact, we have tooling inside Visual Studio where here is an application that I deployed to Elastic Container Service by just selecting our published container. And we have the option to deploy this as a service to ECS. So I could walk through this wizard and go and create my whole cluster and my Fargate class and load balancers and all through this wizard. So go from 0 to a total ECS cluster deployed out there. And when the end result would that be is you will see there'll be a cluster over here which has all of our services. This cluster only has one. I have this guy's running 3 tasks that I all launched using Fargate. And I can get it with my load balancer. This is an application that one of my coworkers writes to find all of the concerts near him. So we did that, deploying that through ECS. So if we go back now and compare our container environments and service environments, looks like there's a lot of similarities. I think that you keep in mind that like the serverless environment, again, everything inside that box though is completely abstracted from you. You don't do anything with that. You just basically handling the events going into there. Versus the container environment, a lot of this inside that box can be managed for you, but you're still going to want to know what's going on, how that's set up for you. So it's going to depend on, come back to your engineering costs. How much do you want to spend on setting up your clusters versus how much you want to hand off to your cloud provider to just take care of everything for you. So then the question is, then what is the right tech to use? And the sad answer is it just depends. There's no single technology that's going to work for every application. You just have to figure out what is the right technology based off of what they can do and what your team wants to spend its time on. I find that most large applications use multiple technologies. You're probably going to have some parts of your application you want to use containers and some you do want to use serverless. In fact, that Gigs for Me application I just showed, we use containers to run the front end, but when you add new users to it or new concerts to it, we need to go do some processing to find out, to let users know when there's a new concert coming in, and that we use serverless for that to go do that asynchronous processing and send those events out to people. So you can find a combination of how you want to do these things. So to break down what we are comparing these, so serverless, we have our continuous scaling, which works really great for spiky or low traffic patterns, because it will instantly scale up for those spiky patterns, and it also means that you don't get any charges for those low periods where you're not doing anything. Because it's serverless, you do have reduced DevOps. We're not managing any machines, making sure they're all patched. I'm not trying to say there's no DevOps. You do always need to make sure that all of your dependencies and everything is still working, but it is a reduced DevOps environment. It works really great for that asynchronous processing where we're just firing off events from our services and we just want that to be taken care of for us. And in many cases, using serverless can be an order of magnitude cheaper to run. Not every case. There are definitely cases where serverless is not the cheapest option, but there are many cases, depending on your application, where it can be significantly cheaper because you're really working with just that spiky or low-level pattern traffic. Now, for containers, this works really great if your system requires you that you need complete control of your compute environment. If you have some sort of compliances or you just have certain ways you want this set up, containers can provide that. If your application is demanding that it has to have a low consistency, a high consistency, low latency, where you can't deal with those occasional cold starts, then containers would be the better fit there. Also, it's cloud agnostic. So if you do not want to get logged into any particular cloud vendor, you can use cloud. Containers does not lock you into that. It also works well, again, we talked about long-running processes versus Lambda is the case where it works for event-driven architecture. Also, with containers, there's no restrictions on which runtimes. With a serverless environment, you're restricted to what that serverless environment can actually handle in its managed runtime. You know, we support .NET Core, Go, Java, and Node.js. But if you wanted other languages, you'd have to find another way to do that. Or you probably would just go use a container for that. Real-time communication, like if we're going to use SignalR or something like that, that's where you'd want to use containers for, not serverless. The idea of serverless is it takes in an event, wraps up in its Lambda function, does all of its processing, and send it back. There's no persistent connection between your client and that compute environment. You would want to have something like containers to provide you that persistent connection. All right, so let's just finish. Let's go check our batch demo to see how that worked out. So if we go back to batch, we should see everything succeeded, which is what we always like to see, that everything always works. And if we went to the EC2 console, we will probably see a bunch of terminated EC2 instances. So it spun up all these EC2 instances, did our batch processing, and then it determined there's no more work to do, and so it took care of deleting those for us. So we don't have these perpetually running. So then if we go look at our DynaDB table, we scan those, we can see that as the .NET dev, that mostly I create .NET Core Lambda functions. So that's what it is. Okay, so to recap, we talked about serverless environments, how those really work, what is the AWS version of that, and that's using Lambda. And we really kind of dived into the life cycle of how that works, even though you shouldn't have to worry too much what's going on inside there, but it's still always good to know how that works. We're talking about how you use .NET Core with Lambda. We also talked about what are the major components of containers and how those compare with a serverless environment. We mentioned AWS Batch, how you can use that as a service with managing all your compute resources and be able to provide that long-running batch process that maybe wouldn't work so well in a serverless environment. Code build is a I kind of think AWS Batch and Code Builder are like a specialized orchestration system. They solve a specific domain, but they're running our containers for us. And then there's Amazon Elastic Container Service, which is the general purpose one that you would use to run all your applications on. And hopefully you got a better understanding of when you might use each of these technologies. What's the right fit for your application's expense? So I didn't get too much to show off these tools, but these are the tools that I work on at AWS. They can be really useful if you're doing .NET on AWS. One I want to highlight, because I know I do a lot of demos showing off Visual Studio and deployments, and most of you are probably thinking, who actually does a deployment to production from Visual Studio? At least that's what I'm hoping you're saying. I think those are really good tools to show to learn how to use a service, but you're going to probably want to use to some automation. So this extensions to the CLI project, what this is all of the deployment features that we add to Visual Studio, we make sure you can use that same code from the command line. So you can transition from Visual Studio deployment and learning how the service works to go and do a deployment from the command line. Like for example, if I wanted to deploy a function, I can run this command here to do that same deployment command. In fact, when I run my deployment wizard, so in that case of my serverless case, this defaults file was written down. This is all the settings that were set up in the wizard. So I can just go straight to the command line and run the same deployment with all these settings. So it allows me to go back and forth. So yes, we do a lot of Visual Studio demos, which again is good for learning stuff. But when you get to your CI system, we can use these tools to go to your CI/CD system. And with that, thank you so much for coming and listening to me talk. There's my Twitter handle out there. I always love to talk about AWS and .NET, so if you ever have any questions, feel free to let me know. I see somebody taking pictures. This link right here is the link to my GitHub repository, which has these slides and the demo code that I showed. So if you guys want to take a look at that, feel free to reach out. And there's some other GitHub repositories that I work on there. And I also am a big contributor in the AWS.NET developer blog. That's one here, so I write a lot about how to do that. And with that, thanks so much for coming.